Good morning, everyone. My name is Claudia, and I'm going to present the work Gas Kinematics and Excitation in the OH Megamaser Galaxy IRAS19154 plus 2704. Luminous Infrared Galaxies, or just LIRGs, are a class of galaxies among the brightest objects in the universe, showing luminosities in infrared bigger than 10 to the 11th solar luminosities. These environments consist typically of galaxy interactions or mergers, and they are believed to represent a key step in the processes of transformation and evolution of galaxies. Besides that, the extreme luminosity in the infrared may be associated with intense star formation and/or the presence of an active galaxy nucleus, an AGN. Here is an example of a LIRG, ZW296, consisting of a pair of merging galaxies. The maser, similar to the laser, is a microwave amplification by simulated emission of radiation. And megamasers, then, are luminous and powerful extragalactic masers with luminosities on the order of 110,000 solar luminosities. They has that name because of the amplified spectral line is due to a transition in the hydroxyl molecule. And they are associated with merged and/or interaction environments, and many OHM host systems present composite spectrum, showing both starburst and AGN features. A possible explanation for that is that galaxies with OHM would represent a transitional stage between a starburst and an AGN. The galaxy from this study is part of a sample of 15 galaxies with OH Megamaser emission from a project whose general objective is to relate the properties of OHM to AGN and/or starburst activity. It is important study to understand the nature of the ionization mechanism of the gas involved in these merged environments and to propose a scenario that justifies the presence of megamaser emission. So we performed a mapping of the distribution, kinematics, and excitation of the gas in this galaxy using integral field spectroscopy. 5 galaxies in the sample have been studied so far, and in 4 of them was detected the presence of AGNs. So this galaxy is a LIRG with luminosity in the infrared of 10 to the 11.66 solar luminosities. It has a redshift of 0.09938, which corresponds to a distance of about 420 megaparsec. The data come from Gemini Observatory and using the GMOS, that is a spectrography operating in optics, in the mode EFU, an integral field unit, that allows performing spatially resolved spectroscopy. So the data reduction is a process that is made with astronomical data reduction and analysis software IRAS. It is a multi-step process with the aim of make raw data that comes from the observatory readable for work. So there are several steps, and the final product of this data reduction is a data cube. So I work with this data cube. And how the name says, it is three-dimensional. So there are 2 spatial dimensions and 1 dimension corresponding to a range of wavelengths. Here is an image to exemplify what I say. Here is a nuclear spectrum of the galaxy. So these lines aquí are the emission lines, and I work basically with them. The methodology is using the EFS cube, is a Python package that allow us to make that fit to adjust these lines. So the gas distribution kinematics is basically fitting of Gaussian curves and Gaussian emit series to the profiles of the emission lines present in the spectra of the galaxy. This gives us two-dimensional maps of flux distributions, velocity fields, velocity dispersions, and Gaussian moments H3 and H4 of the gas for each fitted emission line. And for gas excitation mechanism, we construct BPT diagnostic diagrams. And this allows distinction as to whether the source of ionization of the gas is due to a star-forming region, a starburst, and or an AGN. So here are the results of Gaussian emit. And it is similar to the Gaussian curves, so I'm going to talk about Gaussian curves. And here are the results of the Gaussian curves. We can see that there are two components. Here, the line above is the narrow component, and here the broad component. We can see the peak emission in the core for all lines in both components, and extend emission along the east-west direction. To the velocity fields, the narrow component appears to be tracing the emission from the galaxy's disk and show a rotating disk pattern. And velocity dispersions, the narrow component has lower values for the entire field, and the broad component has higher values. So here the narrow is 50 to 400, and the broad is the 300 to 1000, much bigger. So the BPT diagrams, for both components, most of the points are observed in the AGN region, indicating that the ionization mechanism of the emitting gas of both components is due to the AGN. So this region here is basically an AGN contribution. So the conclusions. We performed a two-dimensional mapping of the distribution, kinematics, and excitation of the gas in the central region of the OHM galaxy IRAS19154+2704. The fit by Gaussian emit series did not result in a representative model of the observed emission lines, indicating that the gas has more than one kinematic component. So we adjust two Gaussians per emission line that fitted, and this proved to be a good model of the profiles at all positions mapped in the galaxy. One of the Gaussians is narrow and the other one is broad. The narrow component is tracing the emission from the galaxy's disk, and the broad component is observed predominantly internal to the 0.7 arcseconds of the galaxy's core, and it is all blueshifted in relation to the systemic velocity of the galaxy and the narrow component. We interpret this component as being to an outflow of ionized gas from the AGN. The BPT diagrams show that both the emission of gas located in the disk and the emission of gas in outflow are predominantly due to ionization of the gas by an AGN. And understanding these outflows and their effects on the host galaxy is very relevant in galaxy evolution studies, as these outflows can stop or induce star formation, depending on the way they interact with the gas of the galaxy. And that's it. Thanks for listening.